So we're going to continue with example 3. A rectangular page is to contain 24 square inches of print. So on my diagram that they sort of provide, this is my print, and this area is 24 inches squared. The margins at the top and bottom to be used are 1.5 inches. You can see we've included that here for the top and bottom margins. And the left and right margins are to be 1 inch. So you can see I've incorporated that above my printed area. What should the dimensions of the page be so that the least amount of paper is used? Now when we're talking about the least amount, we're minimizing the problem. And we want to find the dimensions that minimize the least amount of paper, and the least amount of paper is referring to the surface area, or sorry, not the surface area, it's not 3-dimensional, 2-dimensional. We're referring to the area of the paper being used. So my secondary equation is the printed area. We know that x times y has to be 24 square inches. We know that x has to be greater than or equal to 0, y has to be greater than or equal to 0. Y can equal 24 over x. So that's my secondary. I'm trying to minimize the area of the piece of paper, so I want the dimensions of the full piece of paper. So that would be x plus 1 1/2 plus 1 1/2 is the length. The width is y plus 1 plus 1, so that clears up to x plus 3, y plus 2. Now I have my relationship for y. A is equal to x plus 3. My y is 24 over x plus 2. So that's my area equation in terms of my single independent variable x. Now I'm interested in finding the least amount of paper to use, so I need to take the derivative, find the critical points. But in a question like this, I'm not able to set up any new closed domain restrictions. So I need to make sure that at the very end, I prove that the value I get is the absolute by doing a little bit of some clever math. So let's distribute this out. I get 24 plus 3 times 24 over x. So 24 times 3 is 72. So this would be 72 over x plus 2x plus 6. So I'm going to clean that up a little more. 30 plus 72 over x plus 2x. I take the derivative. Would be minus 72 over x squared. I bring that term up as x to the minus 1 and then take the derivative, plus 2. I set my derivative equal to 0 to solve for x. 72 over x squared plus 2 equals 0. And I solve for x squared. So 2x squared equals 72. X squared equals 36. X is equal to only 6 because we want x to be greater than or equal to 0. So now I'm going to do my number line. I'm going to make sure that nothing is considered before 0 because that's not really possible. 6 is my critical point and I don't have an upper bound, so I'm checking the signs in my area derivative, and then I'm going to say something about the original function. So when I take a value between 0 and 6, like 1, and I sub it into my simplified derivative, minus 72 over 1 plus 2 is a negative answer. And then when I sub in something bigger than 6, I'm going to get a positive answer. So my function is decreasing, then increasing, indicating a local min at x equals 6. But what happens, how do I prove that this is my global minimum? So what I want to try to consider is that this value, when x is equal to 6, is the lowest in the entire function. So what I'm going to do is take the limit as x goes to infinity of my area function, because that's what I'm trying to minimize. And when I do this limit, I get a big number plus 3, which is a big number. 24 over a big number is 0 plus 2, and a big number times 2 is a big number. So that end is going up, and then the limit as x approaches minus infinity would be minus infinity plus 3, which is minus a big number. Minus 24 over minus a big number goes to 0, and 0 plus 2. This limit also goes to infinity. Oh, sorry. Now, I just made a clear error here. I don't want my limit to go to negative infinity because my function is only considered when x is going to 0. So I want to take my limit as x approaches 0 from the right because I'm only interested in what's happening here. I only want to prove that this is a local or an absolute minimum when x is approaching 0 from the right. So when I do that, I get 0 plus 3, which is 3. 24 over 0, slightly positive, goes to infinity, and infinity plus 2 is infinity, infinity times 3 is infinity. So because both of these arrows are going up, this proves that this is my absolute min at x equals 6, and when x is equal to 6, I can take my y, sub it back into my simplified y equation, and 24 divided by 6 is 4. So now the question's asking me what are the dimensions of the page. The dimensions would be x plus 3 by y plus 2. So my dimensions would be 9 inches by 6 inches. And that would be my final answer for that. Let's look at the next example. So 2 posts, one is 12 feet high and the other is 28 feet. So I'm going to make one of my posts here, and this is a fixed 12. And I'm going to make another post over here, which is 28 feet high. They stand 30 feet apart. So the total distance horizontally is 30 feet. They are to be stayed by 2 wires attached to a single stake running from ground level to the top of each post. So there's going to be a stake in the ground. Let's make that my stake in the ground. And the stake is going to have wires that attach here and here. And I want to know the positioning of where that stake should be in order to minimize the amount of blue wire I'm using. So the blue distance is what I'm trying to minimize. The base is going to be x. I'm going to label the location where I put the stake in the ground as x, and then because the total distance is 30, this would be represented by 30 minus x. Now I'm going to call this piece wire 1 and wire 2. I'm trying to use the least amount of wire W, which would be W1 plus W2. Now I need to get that into one variable, and you can see that when I put the stake in the ground and it forms with the horizontal axes, this is at a 90-degree angle, so I can use Pythagorean theorem to represent that. So W equals square root, because I'm looking for the hypotenuse, x squared plus 12 squared, plus W2, which is going to be square root of 30 minus x squared plus 28 squared. Okay, we know that x has to be greater than or equal to 0, but we also know that the stake has to be less than or equal to 30 because the distance between the two poles or the 2 posts are 30 meters or 30 feet apart. So I can't have the stake being put past where the distance between the 2 posts are. So there's my equation. I managed to get a closed interval, so I don't need to do proving of absolute maxes and mins. I just need to do my critical points and my endpoints and test the lowest one because I'm doing the least amount of wire. So I'm going to take my derivative, which will be chain rule. I have a square root. The square root is 1 over 2 something to the minus 1/2. So I'm going to just automatically put it on the denominator. The derivative of the inside is 2x. So there's my chain rule. Plus my derivative of the second term is 1/2 square root or 1/2 times the stuff to the minus 1/2. And I'm automatically going to put that stuff on the bottom with the square root over it. Hopefully you've done this derivative many times. And then the derivative of the inside is chain rule. So it's going to be 2 times 30 minus x. And the derivative of 30 minus x is minus 1. I want to set this derivative equal to 0 and then solve for x. So what I'm going to do is I'm going to do w prime equals 0 implies. Now I'm going to make this entire w prime expression equal to 0, but because this term is negative, I'm going to take this whole second piece and move it to the other side. So when I set it equal to 0, I'm going to get 2x over 2 square root of this stuff equal to 2 times 30 minus x over 2 times this stuff. So it's just like me moving that term over. I kind of just skipped a step there. Now you can notice that there's a 2 in the top and bottom here and here. So I'm going to cancel them out so I don't have extra terms to deal with. And I'm going to kind of multiply both sides by each of the denominators. So I'm going to get x times, or actually before I even do that, I can square both sides. So I'm going to square the left-hand side, which will give me 12 squared. And I'm going to square the right-hand side, which is 30 minus x squared, divided by my denominator, which is 30 minus x squared plus 28 squared. Okay, we're going to equate these two things together. So x squared 30 minus x all squared plus 28 squared is equal to x squared plus 12 squared times 30 minus x all squared. Let's kind of clean that up a little bit. So when you take these equations and isolate for x and actually solve this equation, which I kind of don't want to do, it's a lot of work, but you can notice just kind of briefly that this term times this term is the same as this term times this term, so those would cancel out. And then when you clean it up and isolate for x, you're going to get two answers. You're going to get x is equal to 9 and x is equal to minus 22.5. And I'm just going to put solve carefully, which I'm going to let you guys work through now. And when we solve that carefully, this is what we get. But we know that x cannot be negative, so that one's gone. So I literally have my end point, which is 0. I have my critical point, which is 9. And then I also have my other end point, which is 30. Now when I sub these in to my w function, which is this one in blue that I'm kind of boxing in, what you get is this one is 53, if my math was correct at the point I did this problem on paper. This would give me 50 and this would give me 60. Now by the extreme value theorem, my absolute min will be the smallest number out of those, and it will happen when x is equal to 9. So what that means is that, and I'm verbally going to state the answer and you would want to just write a sentence out. If I put my stake 9 feet away from the post that is 12 meters high, that is going to make sure that the amount of wire I use is at a minimum. And I'm using the least amount of wire. And who says you don't use math in the real world? Okay, now this problem is a key problem. And the reason that this one is really funny is because normally when we do absolute max and min problems, the majority of the problems we find that the critical point gives you the absolute max or min, and it's just a matter of trying to be fancy to sometimes prove it's the absolute max or min. but sometimes you can just use extreme value theorem. This example is quite good because the maximum actually occurs on an end point and not on the critical point. So this is a really good example to pay attention to. I remember seeing this on a future exam for students that I used to TA in post-secondary, and their teacher had posted this on their midterm. So we have 4 feet of wire, and we're talking about an amount of material, which is kind of referring to air or perimeter or circumference in this case, is used to form a square and a circle. So they're giving me information about perimeter. So I know the perimeter of my square is 4x according to the variable they defined. And the perimeter of a circle is given a fancy name called circumference, and the circumference of a circle is 2 pi r. And in total, we have 4 feet of wire used for both. Now, how much of the wire should be used for the square and how much should be used for the circle so that we get a maximum total area? So my primary equation is area. The area of the square plus the area of the circle has to be a maximum. Okay, so we know that r has to be greater than or equal to 0. X has to be greater than or equal to 0. We're going to take our secondary equation and isolate for one of the variables. Now, it doesn't matter which one you isolate for. The one I'm referencing here, I isolate for x. So I'm going to get the x by itself, which would mean that I'm going to subtract over 2 pi r from both sides and then divide by 4. And we're going to notice that this, and this coefficient are all divisible by 2. So I'm going to go ahead and clean that up and divide all of them by 2. Now this is an expression for x, so I also know that 2 minus pi r over 2 has to be greater than 0 because x is greater than or equal to 0. And when I isolate for r in this case, I get that 2 is greater than or equal to pi r. So 2 over pi is greater than or equal to r, and r is less than or equal to 2 over pi. So the nice thing about this example is that I'm able to set up a closed domain on r, so I'm allowed to use extreme value theorem. So let's go ahead. We need to use extreme value theorem, which means I need to find my critical points by taking my derivative and setting it equal to 0. So my area is x squared, which is this expression I just found. So 2 minus pi r over 2 squared plus pi r squared. So one cleanup step, the denominator expands out to 1/4. We get 2 minus pi r squared plus pi r squared. I'm going to circle this equation because we're going to reference it later. That's my simplified area equation. I'll actually color it in. Let's take the derivative. So a prime, it's going to be chain rule. I'm going to bring down the 2, so that's going to simplify to 1/2 2 minus pi r to the 1 times the derivative with respect to r is minus pi plus 2 pi r. And I want to take, where does a prime equal 0? I'm going to multiply the whole entire equation by 2, and I would get 2 minus pi r times minus pi is equal to 4 pi r, or, well, I should be careful, plus 4 pi r equals 0. I'm going to move this term to the other side, so 2 minus pi r, it's a negative sign, so I'm going to just change it to a positive sign, equals 4 pi r. Divide both sides by pi. R is equal to 2 minus pi r. Oops, I have to be careful here. So I want to move the r terms to the same side. So 2 minus pi r equals 4r. So I move the pi r to the right and factor out the r. And I get that r is pi plus, whoops, I'm making a lot of careless errors here. 2 divided by pi plus 4 is my critical point. Now if I work out that number, it's going to be 2 divided by 4 plus pi works out to approximately 0.28. When I do 2 divided by pi, I get 0.64 approximately. So that means that this would be a critical point. So now I need to try my end point, my critical point, which was 2 over 4 plus pi. And I need to check my other end point, which is area at 2 over pi for r. And I'm subbing it into this equation in yellow here. So when I do that, I'm going to get a of 0 to be 1. I'm going to get this one to be 0.56 approximately. And the last one, when you sub that in, you get approximately 1.27. And we're subbing it into that equation. So you can see here by the extreme value theorem, my absolute max is actually happening on the end point when r is equal to 2 over pi. So when r is equal to 2 over pi, I'd like to solve for x, which would be given by this equation in green. So if I sub x in there, so if I take 2 over pi, sub it in, so I get 2 minus pi times x, 2 minus pi times x, divided by 2, I actually get x is equal to 0. And that's producing my absolute max. So it's saying that x is 0, no wire to square. So that means all the wire is going to the circle, and I'm producing the absolute max. Now, in this final example, you can sort of see that they present a problem. They've given me the solution here on this bottom page, but I kind of want to point out a little bit, and I'll set up the problem, but we're not going to fully finish solving this problem. So basically, they say a cylindrical can, so just a can, is to hold 1 liter of oil. So my volume is 1 liter. Now the problem is we want to minimize the cost of the metal to manufacture the can, and the can dimensions are going to be in a linear measurement like meters or centimeters. So what I need to do is I need to relate my liters to a known linear quantity. So 1 liter is 1 meter cubed, or 1 liter is 1,000 centimeters cubed. Now in this question, the solution that this text had presented had used that the liter was 1,000 centimeters cubed. Now, when I do this problem, I don't want to make the problem more difficult for myself, so why not use that 1 liter is 1 meter cubed? My numbers are a bit simpler to work with, so that's what I would do with the solution here. So the volume of a can is the area of the base, which is pi r squared. And then the height of the can is h. So that represents my volume, and I'm going to use the 1. So I can rearrange for h. It's 1 over pi r squared. There's my secondary equation. We know that h has to be greater than 0, r has to be greater than or equal to 0. My primary equation is to minimize the cost. Now, in some of these problems, the cost to make the material on the top can sometimes be different than the cost on the sides. So you want to make sure that in this question, we're going to assume that the cost to produce the can is the same regardless of the top, the bottom, or the sides. And I'm going to call the cost per meter cubed. So cost per meter cubed, I'm going to call that C. So that's going to be a fixed number, like maybe 20 cents per meter cubed or something of that sort. So what I want to do is calculate the surface area of the can, which is the area of the bottom, pi r squared, the area of the top, which is another pi r squared, and then when you open a cylinder up, you almost get like a piece of paper, and that piece of paper, when you open it up, represents the circumference of the circle, and then times the height to produce that. So this is what it looks like when you open it up, and this is 2 pi r because it was the circumference of the circle, and this was h, and then the area of a rectangle is 2 pi r h. And now my cost equation is going to be this surface area multiplied by cost. So I'm going to call, actually what I'm going to do is I'm going to call the cost per meter cubed little p. So I'm trying to minimize the cost, which I'm going to call capital C, and it's going to work out to little p times 2 pi r squared plus 2 pi r h, and then this is the equation that I would go ahead and maximize or minimize, in this case minimize, so take the derivative, set it equal to 0, find the critical points, and so forth. But the solution that this textbook decides to present to you is taking the surface area and minimizing the surface area equation, which is represented by, let's use yellow, by this equation, and you can sub your h in. And so they present the solution where they use 1 liter is 1,000 meters cubed, so they get a similar equation. They isolate, get a similar equation. They sub it into their area, get a similar equation to ours, which I haven't done. And then they take the derivative, set it equal to 0, and solve from there, just like we normally would. But the thing in this problem is that they're minimizing the area, and some of these problems, minimizing the surface area doesn't always necessarily mean that you're minimizing the cost. So I feel like we should have approached the problem in this way, and in this way it won't matter in the solution because this cost is multiplied by the whole equation. So I can just take my surface area, and minimizing my surface area would also minimize my cost in this case. So, but they end up minimizing the area, so they get a critical point, and we're going to just kind of walk through this solution here. They set it equal to 0, they solve that equation, and they get r is equal to the cube root of 500 over pi. Now what they do is, that's just a critical point. We weren't able to set up a closed domain, so we're not allowed to use extreme value theorem. So we need to be a little bit clever in proving how this is the absolute minimum. So we could argue that if I do the limit as r approaches 0 from the right, which is sort of what we were talking about before, my domain is 0 onwards. So I could do 0 from the right, and then as x approaches infinity, and we'll find out that both of these limits end up going to infinity, so that the local minimum that we got with this r value ends up being the only critical point. There's no other things in there, and it ends up being my absolute min. Now once you get your r value from setting it equal to 0 and then proving that it's the absolute min, you can just sub it back into your h equation. Theirs is 1,000 over pi r squared. Ours is 1 over pi r squared, and then you can get that the height is equal to twice the radius, and that would end up minimizing the cost. But again, in a problem that I could present to you, if I tell you that the cost to produce the top is different than the cost produced needed to produce the sides, you would need to find the cost equation to minimize or maximize. So just be aware, I don't like how this part of the solution is presented, because in these sort of problems, you're not minimizing the surface area, you're minimizing the cost. But in this very specific example, minimizing the cost is equivalent to minimizing the surface area. And that's that.